Welcome, everyone. So the speaker today is Kate Turner, and she will count the ways for why Q should equal P in the Wasserstein distance between persistence diagrams.
Oh, thanks, Sarah, and thanks, Henry. So yes, I guess this is a talk with a slight political bent. I'm going to try and convince you of my perspective on a choice you can make in sort of one of the more fundamental definitions within algebraic applied topology. So this is something that occasionally people have asked me about because I have a position that's slightly different to, I guess, the historical first option. Let's remind ourselves what Wasserstein distance is. So this is, a distance between persistence diagrams, and we have two different persistence diagrams, and we look at all the possible ways we can match up the points. We then have to choose what metric we're using in the plane, and that's the Q, and then we have to decide what the power of it is, and that's the P, okay? So we're looking at the screen, and I'm like pointing at things. But the key thing is that if we take the limit as P and Q both go to infinity, all right, we end up getting what we're used to with the bottleneck distance. So we look over the infimum of all possible matchings, and then we're looking at the largest difference in terms of either births or deaths within that matching. So let's remind ourselves with a picture. So we have two diagrams here. We have a square diagram and we have a triangle diagram, okay? And the way we do a matching is we just basically make a bijection between the points in the square diagram and the points in the triangle diagram. And because this is persistence diagrams rather than Wasserstein distances between measures or something like that, we actually have this complication to do with the diagonal. All right, so everything can match to the diagonal if you want. So our diagrams can have different number of points, et cetera, et cetera. But the key thing is that we kind of are pairing up things where either you're a point off the diagonal or you're a copy of the diagonal. And so every time we have a matching, this is like a transportation plan from one diagram to the other. And so our Wasserstein distances are looking at the smallest cost transportation plan. Okay, so let's remind ourselves of the bottleneck distance. All right, so this was the historical first, this is what people looked at. They took their matchings and then they took the L infinity norm in the plane and they took the largest over all of them. And people love the bottleneck's distance because it's, known to be stable under a variety of things. So I think it was first proved for sup norms of sublevel set filtrations of functions. People have also done it in terms of bounding the difference between the diagrams from Rips filtrations in terms of the Gromov-Hausdorff distances between the metric spaces. There's also a ton of other stability results of other systems, whether you're doing, check or if you're doing just a symmetric function, it doesn't necessarily, have to be a sublevel set over the same space. Okay, so, but the key thing is, people like it because it's stable, and people also like it because it has nice theoretical properties in terms of algebra. So people have studied the interleaving distance between persistence modules and have shown that it gives you the same thing as the bottleneck distance between their corresponding persistence diagram. Okay, now...
Kate, question.
Yes.
Would you consider this an example of P equals Q? They both equal infinity?
They both equal infinity. Amazingly enough, P equals Q equals infinity. Yes. This is a P equals Q. So the first case was P equals Q. All good, all right? And so just reminding ourselves what the roles were, okay? So we had our P is the power and our Q is our metric in space, all right? So the Q is a very local thing, it's down to each pair of points, whereas the P is a more, I would say it's more fundamentally important. So it's telling you about how important long distances are versus short distances, okay? So if you're looking at P equals 1, that's one extreme, lots of short bars make a difference. If you're looking at P equals infinity, all those short bars count for naught. Okay, so they're the two extremes. And what I would like to argue is that if you fix your P, the Q, it doesn't matter so much. So for a talk about why Q should be a specific thing, I'm now just giving a talk, a slide about why it doesn't really matter. Because the key thing is that when you're looking at these metrics in the plane, they're all by Lipschitz equivalent. Okay, so if I take 2 points in my above the diagonal or the diagonal, then if I change Q, I'm only changing it by at most a factor of 2. Okay, it's usually less. The 2 here is worst case scenario when we're looking at 1 and infinity. If they're in between, it's some power of 2, which is less than 2, but that doesn't matter. But the key thing is that because we have this by Lipschitz equivalence for a pair of points, that just it induces a by Lipschitz equivalence for the Wasserstein distances themselves. Because if you take a particular matching, then the cost of that matching under these different transportation plans is sort of by Lipschitz equivalence. So when you take the infimum over all of them, you also get this by Lipschitz equivalence. So I guess the key point of this slide is basically to emphasize that you're not losing anything by changing your Q. I have mentioned why I want Q to be P. To some people, they go, oh, but Q equals infinity is stable. And it's like, well, not really. Q is infinity is stable only because the P was infinity, not because the Q was. And so any of that analysis, the difference is not huge in terms of actual, magnitude of numbers. It's more the properties that will be nice. Okay? So does anyone have any questions about this by Lipschitz equivalence before I head on? No? All good? I'm preaching to the converted. All right, I just wanted to make a point here. We can ignore this slide if people don't want to, but often we can talk about a specific persistence diagram by fixing a homology dimension or because we had a persistence module constructed however way, which was not from persistent homology. Or we can say, all right, I've got some sublevel set filtration or a RIPS complex, and I have all the different homology dimensions, and I might want to consider them all simultaneously. You can define, a PQ Wasserstein distance over all of them simultaneously or individually. It doesn't really change things that much. Okay, so what are the main contenders? So historically, the Wasserstein distance was first defined with the P that varied, but the Q was always infinity. Didn't matter what P was. Okay, so they took bottleneck distance and they said, well, we want something with a different P, which is not infinity, so we'll just change the P bit. Okay, so I'm not completely privy as to the reasoning behind this, but my guess is they just didn't consider that you could change the Q. I mean, it was just one parameter and they wanted to change it as minimally as possible, I guess. So I think this was in the Lipschitz stability paper. I might be wrong in terms of the first origin of Wasserstein distance for persistence diagrams. I'm happy to be corrected. So I guess the main contender that I would like to argue for, so the one I'm rooting for, is for Q to be set to be P. And I've started seeing more papers mention that, though Q equals infinity does seem to have a stronghold, and I think that's partially because the code has often Q equals infinity, with the exception of Irene. I have also seen Q equals 2, but that's rarer. So those are the two things. So I'm going to be basically comparing Q equals infinity to Q equals P throughout the rest of this talk as a rule, just because that's the most blatant comparison, and it's easier if you're only comparing two things. Okay? So why should Q be set to P? So I tried to count the ways. So I've come up with 5 reasons which are related but somewhat different, in flavor. And they all kind of point towards why I should make Q equal P. I am yet to find a reason for why I wouldn't want Q to equal P, but I'm happy to hear any arguments. So I'm just going to go through these basically for the rest of the talk. So if you get a bit lost in one of them, you can kind of tune out until we get to the next number. So the first one is the simplest, formulae nicer, okay? So I'm just going to put the 2 formulas down. And that's my only slide for this section. But if you look at the p equals infinity case, you have this infimum out the thing, that's always the same. And then I have a sum of a bunch of maximums, and then I take a power. I mean, it's all kind of mixed up and gross. You know, I have to take two numbers, I have to compare them, I then take a power, I then sum them up, and then I take a p through, all right? Now, if I make p equal q, all right, if I have q equals p, I should say, then what happens is that that norm of in the plane actually splits up. Okay, so remember in your definition of Wasserstein, you take your norm, your q norm to the power of p. Now, but if it's a p norm to the power of p, well, that's just the same as the differences in the x coordinate to the p plus the differences in the y coordinates to the p. So what you end up happening is that they actually split up. You have these two separate sums of p powers. So you can basically say that I end up really having something that looks more like an LP norm generally, where I've kind of split up the coordinates separately. Okay? And I personally think this is a much more attractive formula, but I guess that is a matter of taste. All right, so that's my first point.
Kate, can I ask a question here?
Yes.
So you're comparing p infinity to pp, but if you were looking at the pq case,
yes,
you know, this max and this infinity would have like these qth powers and then a qth root out front, and
yeah,
is it
so
sort
it
of
looks
like
even worse when you take q to be neither p nor infinity. You get like a sum of square roots of things. It's just you get a factor of q divided by p somewhere. You know, p divided by q somewhere. It's even grosser. You know, it's in a way, you know, the p equals infinity is the nicest of the non-p q equals p case. It only gets worse. Yeah. All right, so it better reflects the geometry. So this relates to the breaking up of this formula, all right? So the idea is that each coordinate has a separate meaning, okay, and they're infinitesimally independent. Okay, I have a birth event and I have a death event. These aren't like they're points in the plane and the coordinates don't matter. The coordinates matter here. They've got meaning. It's not like I'm just taking 2 points in some arbitrary metric space. So they have a meaning. So if I have a local change for a single critical value, it will either affect the birth or the death. It won't affect a combination of them. So I'm going to be changing either the birth coordinate or the death coordinate. Okay, so this is quite different to looking at points in the plane generally. Okay, so this is sort of an important thing to think about, whether we want to be able to split up those births and those deaths. So I've just got an example here, so I apologize that I wasn't going to code up the pictures. So I've got a height function here, and I'm going to just look at, I'm just looking at zero-dimensional persistent homology with a height thing. And so my purple curve is sort of the first, you know, my initial thing. And then I could think about perturbing it in different ways. So I could perturb it by moving up this bit on the red, and that changes just the death coordinate of one of the points. And so you can see that you're just moving up in the diagram. And then if I look at the blue and the green, okay, so these are two different perturbations that might happen at the same time. Now, as the blue goes down and the green goes down, all right, I'm changing both the birth and the death coordinate, but they're kind of changing independently, okay, because the change in the birth is to do with this region all the way over near the blue, okay? There's no reason why this section near the blue should be affected by the section in the green, all right? And then if I'm perturbing near the green, I'm changing the depth value. But again, there's no reason to suspect that that change in the depth value would be affected by a change in the blue value. So sort of locally, these values of the coordinates for these bursts and the deaths are kind of acting independently. Okay, globally this is not true, but locally they're having this kind of effect. All right? And you get the same kind of effect happening with point clouds if I'm doing a Rips filtration or something like that. I've got some cycle. It's going to occur at the distance between a particular pair of points. Okay? So if I've got this first example here, and I apologize, it's not actually a Rips filtration. I just drew in edges by eye. So I have this critical 1 cell between X and Y that's giving birth to an H1 class. All right, and this H1 class lives for some time until a different edge comes in. Now that edge may involve X or Y, but it could be a completely different pair. Okay, so, I mean, it could be that they are related to each other. It could be that they both involve X or something, but it could be that they're completely different. And so your birth time is dependent locally on these positions of a particular pair of points, and your death time is dependent locally on the positions of a completely different, potentially a completely different pair of points. And so if I'm wanting to look at the distances between their respective diagrams, then it's sort of like those are kind of acting somewhat independently. And so I want my distances to be able to take both of them into account, not just the maximum. Okay? So I want to be able to look at how much that edge changes plus how much. So how much XY changes and how much AB changes, not just whichever one happens to change the most of the two. Okay? So I tried to try and make this a little bit more formal in terms of sublevel sets of functions on a simplicial complex, and this will relate to point 3. Okay, so if I have a simplicial complex and I have a function defined over it where it's injective, okay, so these things can be generalized to where it's not injective, but it's clearest when it's injective. Okay, so every simplex has its own function value, all right? And then if I look at the persistent homology from this, I can say, well, for every point in the persistence diagram, there is a specific simplex which corresponds to the birth, and there is a specific simplex that corresponds to the death. Okay, so I've written this as sigma as tau. So for each point P, there is a sigma of P and a tau of P, and they are the simplices, in some sort of, Morse, discrete Morse theory kind of way, that are critical cells. Okay. Now, if I wibble F a bit, okay, if I change F just slightly, okay, those order in which the cells appear are going to be the same, and so which things are critical are going to be the same. I'm going to have the same kind of behavior. It's just the exact times are switching. So what ends up happening is that I could take the diagram for F, and I can say, well, every point is going to be the function value of a critical simplex, function value of a critical simplex. Okay, and instead of that function being F, it's now just G, where G is something close to F. Okay, so if I'm wanting to, if I'm wanting to describe how things are changing, if I'm wanting to take the distance between these two different things, I'm wanting to describe it by both those changes in sigma, the function value on sigma and the function value on tau. I don't want to just take the maximum of the two. I wanted to consider both of them. All right. And again, just like in the RIPS or in the, the sublevel set for the function, there's no reason to suspect that the function value on sigma, locally is affected by the function value on tau. Okay. I mean, there may be circumstances where, they set up and there's some global interaction, but generically, locally, you expect them to be somewhat independent. Okay, so this will take me to point number 3, that I certainly believe that the p-Wasserstein distance, rather than the p-infinity Wasserstein distance, is sort of the natural version for where stability theorems should lie. Okay, and this relates back to this thing here. I went forward instead of back, and yet it's the same slide. Crazy. It relates to this idea that locally it's dependent on these change of function values on critical cells. Okay? So I'm going to just give you a little argument as to why you would have a local stability theorem for sublevel sets on a simplicial complex. So I'm fixing a simplicial complex and I'm looking at different functions over the same simplicial complex, okay? And those functions are really close to each other, so close that they actually keep the same order of the cells, okay? So my diagram, G, is going to be such that every point in G can be thought of as the function value on the corresponding critical cells for the diagram in F. Okay, I hope that first line makes sense. For every point in F, I have a point in G where all I've done is replaced F with G as, over those particular critical cells, all right? And so this sort of indicates a really kind of obvious matching, all right? I match the points in G by just taking, the ones over the same pairs of cells, okay? And so if I take the cost of this matching, all right, so I'm taking the P cost here, all right, so the PP cost, I'm getting the sum of the differences in the births to the P plus the sum in the differences of the deaths to the P for these sorts of critical cells, okay? All right, so in the end, what happens is I just sum over every critical cell and I take the difference in the function values. Because I can split up the births and the deaths as separate, I can kind of forget how they were matched up because I get the same value if I just sum over the critical cells. All right, now if I sum over the critical cells, then that's, upper bounded by summing over all the cells, okay? Because, when we look at these homology classes, there'll be, you can pick an injective choice. You only have one homology change whenever you add a cell in. So it means that what I can do is I can say, well, the cost of this matching is bounded by an LP distance between the functions. Okay? Now, it is true it will also be bounded by, the Wasserstein P infinity will be, but that's because we've kind of, the P infinity distance is always smaller than the PP distance, or is always bounded by the PP distance, because you're just sort of neglecting the smaller values. Now, it makes sense since we can put these smaller values in anyway. This is sort of a more natural setting for putting the stability theorem in. Okay? So the key takeaway is that if you've got two functions over a simplicial complex and they're close enough, okay, then the Wasserstein distance between them is going to be bounded by the LP distance between the functions. Okay? Any questions while I drink coffee? No, it's all good.
I guess I maybe have a question. So, the stability for sublevel set persistence in the infinity sense is maybe simplest. In some of the original papers for Wasserstein stability, it's more complicated, or do they have extra restrictions? Off the top of my head, I don't remember what
so the only Wasserstein stability theorems out there currently, I mean, this isn't out there currently, are for Lipschitz functions. They're not over simplicial complexes. And there are a whole heap of restrictions, partially because, well, you can find counterexamples if you make your P small enough. So they're only true for sufficiently high P to start with. And so they don't come out nicely, and they're much more work than this.
And those extra assumptions are needed when the orderings of the simplices can change too, as you perturb further.
That's not the issue. The issue is more if you've got Lipschitz functions over say a manifold, you can have lots of tiny peaks, and you can fit lots and lots of tiny peaks in. And so that means that if your P is too small, you can end up making your Wasserstein distance go up to infinity without changing, while still bounding the function distance.
Right.
So it is a fundamentally more complicated problem.
Thanks.
Yeah. All right. So your point about the changing of the order, I mean, this is a relevant thing. But the key thing is that it doesn't cause us problems. So this sort of local thing does extend to a more global thing. So if you have two different functions, then you take your sublevel set, persistent homology, then the Wasserstein distance between the diagrams is still bounded by the function norm over the simplicial complex. So I can give a little mini proof. The mini proof is take linear interpolation and split. So if I've got two functions here, okay, so I can sort of think that I've got functions FA and FC, all right? And then if I do some sort of linear interpolation between them, occasionally they'll intersect and they'll change order, okay? But it will only change infinitely many times. I've got a finite simplicial complex, there's only going to be finitely many times where these order changes happen. And so you just do your little local result on every sublevel set, on each of the subintervals, and add them up. So going from the local to the global is actually not too much of a problem. So I know that this isn't really to do with P equals Q equals P versus infinity, but I thought I may as well stick in some corollaries of this while we're here. So if you have Lipschitz stability over a fixed simplicial complex, you might think this isn't particularly useful, but in fact you can massage it to a bunch of different applications, such as image analysis, or for the persistent homology transform, or for Ripps complexes where you have some uniform bound on the number of points. So you can massage it to a bunch of different applications, which is kind of useful. And arguably in all of these cases, you're wanting the WPP rather than the WP infinity, because it's sort of the strongest version of stability that you can get. All right, number 4. All right, so I guess, those who are interested in applications and, statistics and stuff may be quite happy with the stability, but for those who are more sort of theoretical foundations inclined, we want to be able to have something that's very algebraically satisfying, okay? And I think that this is, in a way, the best argument for PP rather than P infinity, is because there is this really satisfying algebraic setup for persistence modules, that kind of comes out naturally when you do this. Okay, so just a reminder for anyone who doesn't know or has forgotten, your persistent module is your family of vector spaces, and you have these linear maps that go between them, all right? And so often what we want to do is we'll take persistent homology of this, so our vector spaces will be the persistent homology at some parameter value, and then these linear maps are the induced maps by inclusion. And sort of the loveliness that is representation theory gives us this wonderful interval decomposition, and those intervals correspond exactly to the points in the persistence diagram. Okay? Now, one of the things people like about persistence modules is you can, instead of, just thinking about I have a point here and a point here, and it sort of seems slightly arbitrary, you can think of these things in a more sort of functorial way, and you can have these sorts of maps between different persistence modules, and we will see that, the bottleneck distance corresponds to properties of this. So one of the things that's most common is these interleavings. So we can say two different persistence modules are epsilon interleaved if there's appropriate morphisms kind of between them, but they're not morphisms in the classical sense, in that you keep the t the same, but rather you shift them. Okay, so you always sort of go forward by epsilon when you go along, and that kind of gives you a bit of freedom, a bit more freedom than if you were requiring them to be morphisms between them, okay, which I'll discuss later. But the key thing is that the interleaving distance can be defined as the smallest epsilon where you can interleave them. And then your bottleneck distance is shown to be this interleaving distance, that these are kind of equivalent metrics. If you were to take your persistence module and make it a diagram, then the interleaving distance between the original persistence modules is exactly the bottleneck distance in the diagrams, okay? Now, unfortunately, although in the diagrams there was this kind of obvious, in quotation marks, generalization to Wasserstein distances by taking sums of distances and stuff like that, there's no obvious choice for the interleaving distance because that required that constant shift. You couldn't define it so that at in one bar I shift by epsilon, and then another bar I shift by 3 epsilon because I needed to go that little bit further for that point in the persistence diagram. You can't split it up that way. They always have to go the same amount. So it's not a good setup to try and generalize to Wasserstein distance when your P is, oops, that's meant to be infinity, not 0. Oh well, there you go. There's my first mistake. All right, so what we're going to do is we're going to try and step back and ignore interleaving distance and go back to persistence modules and their structures and try and think of something which does that does generalize. So an alternative description that will give us the same thing as the interleaving distance or the bottleneck distance, but is generalizable. So the first thing I'm going to say is that one thing you can describe about a persistence module is you can say, well, what's the longest bar? That's certainly related to the bottleneck distance. I mean, it's double the bottleneck distance, but to the empty persistence module, the zero persistence module, I should say, or the empty diagram. But this is something you can certainly talk about in terms of a P generalization. So the P norm is something I've seen. I've seen other words used to describe the same thing, but you basically just take the sum of the lengths to the P, take the Pth root. So if P equals 1, I'm just looking at the sum, the total persistence, I think is what they do. It's called sometimes. So you're just looking at the length of each bar, thinking of that as a number, and taking the P norm effectively of that. All right, so this is something that does generalize. So we've at least got something to work with. Now, we want to work with morphisms. Morphisms are great. So let's remind ourselves what a morphism is. So a morphism between persistence modules is now going to be a family of homomorphisms, or I guess linear maps, because these things are vector spaces. And so you keep the T the same, all right? But the key thing about morphisms for persistence modules is they have to respect those transition maps within the persistence modules. Okay, so we need this commuting diagram. So if I go down into B, it has to, I have to go across and down. It's the same as down and across. All right. So you can do algebra generally with morphisms, and you can talk about isomorphisms. You can talk about kernels, and you can talk about co-kernels. It turns out that the kernels and the co-kernels of morphisms are themselves persistence modules. They have nice-ish structures. So let's just have a little example. So, I mean, you don't have to have persistence modules sending one interval in the decomposition to another interval in the decomposition, but it does make life a lot easier for describing in pictures. So that's what I'm doing in this talk most of the time, and then I'm going to wave my hands and say it works generally. So here's an example where I've got two quite boring persistence modules. I have a single bar in each of them. So A is a persistence module that goes from A1 to A2, and B is a persistence module with a single interval from B1 to B2. Okay, I could be careful about endpoints, but I'm not. So what I want to think about is there is a trivial morphism, which is a really boring one where everything gets sent to 0. So we're going to ignore that. We're going to try and look at the non-trivial one. And because of our commuting map conditions, basically it means that the thing that generates the bar in A gets sent to something that generates the bar in B. So everywhere along down there, and it has to be basically the same generator because I have the identity map in the right direction. So all my maps in the right are the identity. So I can't change which generator it goes from one to the other as I go along. There's just like a single choice. Okay, so there's a single, up to isomorphism, there's a single morphism, non-trivial morphism between these two persistence modules. Now, if we want to look at this non-trivial thing, we have a kernel and a co-kernel, and they're isomorphic to persistence modules of a single bar. So before I go to the kernel and co-kernel, it's worth noting that your birth and death values can only get earlier, all right? A1 has to be later than B1, or otherwise that first thing has to go to 0, all right? Because that thing in A1 has to go to something in B, okay? And furthermore, B2 has to be earlier than A2, or otherwise, again, we're going to have issues with those commuting maps in the morphism. So if you see this morphism here, that's going to force that birth and death times can only kind of shift backwards, all right? They're the only options. Now, when we look at the kernel, we're looking at the things that get sent to 0. So it's going to be the difference in the death times. Okay, it's going to effectively be an interval module which goes from the death time in B to the death time in A. All right, and when we look at the co-kernel, it's going to be the difference in the births. Okay, they're going to be from the birth time in B to the birth time in A. Okay, so there's very little option in terms of what happens when I just have a single bar in each. Okay. Now, unfortunately, if we have two arbitrary persistence modules, we can't really expect to take a distance between these modules to be reflected in a single morphism. Okay, we would want to say, all right, we've got some matching of our intervals. I want my morphism to work with these matchings of the intervals, but those shifts in the births and death values to be only earlier means we can't do that. If I want to make something which doesn't have that both shifting backwards property, like in this one, then there's no way I can make it part of a morphism, all right? So the solution to this is to say, all right, I'm not going to expect there to be a morphism that goes from A to B that will reflect what I want in terms of matchings in some way, but instead I'm going to say, all right, I'm going to take a third object, all right, that's going to have morphisms to each of them, and I'm going to make it so that that those morphisms are going to exist the way I want. So this interpolating object I'm going to use, I'm going to make sure its endpoints are late enough that it can send things to both A and to B. All right, so this is what we're going to define as the span of two persistence modules, sort of standardish notation for things within homological algebra generally. Okay, so this is not exactly, this span of modules is not a new concept. So the question is, how do we construct a span from a matching? All right, so I've taken my sets of, I've got a blue diagram and a red diagram, and I apologize to anyone who's colorblind. And in every pair, I want to be able to say, all right, I'm going to add an interval to C. And that interval in C is going to go to the red one. So say A is red, it's going to go sent to the appropriate interval in A here, and it's going to get sent to the appropriate interval in B, okay, which will be the blue. So if I take this, if I take the top rightmost matching, you can see I've got a red one and a blue one that are matched together quite off the diagonal. I want to have effectively a third point, all right, which is a shame I haven't drawn there. Oh, look, I'm sharing screen so I can show that. So I want a point kind of here, okay, so that its birth time is at least as late as both of them, and its death time is at least as late as both of them. So this point here is going to send down to here and to here, and those will both make sense within a morphism. Okay, so for this pair, I'm going to add a point here. For this point, I'm going to add a point here. For this point, I'll add a point here. For this one, I'm going to add a point here. For this, I'm going to add a point here. And this, I'm going to add a point here. Okay, and then each of these points, I can say, all right, I take an interval corresponding to that point in the plane, and that's going to be one of the intervals in my interval decomposition. All right, so let's just see it for a particular example, just a single boring, back to the one boring bar in each example, and just bottleneck distance. All right, so A is a particular bar and B is a particular bar, all right? And I'm going to make this interpolating thing C, all right, where the birth of it is the maximum of the two birth values, and the death of it is the maximum of the two death values, all right? Now, there is no morphism from B to A or from A to B, no non-trivial one, but there are nice non-trivial ones from C to B and from C to A, all right? And again, just like in that first example we saw where there was a morphism, the kernels and the co-kernels of different things correspond to these differences in births and deaths. Okay, so if we look at the kernel from C to A, it's exactly the change in deaths. And if we look at the co-kernel from C to B, it's the change in births. And the other two are zero. Okay, the kernel from C to B is empty, and the co-kernel from C to A is empty. Okay, so what we have is that the bottleneck distance between A and B is going to be the maximum of the norms of these kernels and co-kernels, because it's the maximum shift in either births or in deaths. Okay, and I think it should be clear in a bottleneck distance kind of scenario, because I'm taking maximums, if I take A to be the union of 2 bars and B to the union of 2 bars, and I've matched something here and I match another pair somewhere else, well, I'm taking the maximum of a bunch of different things. It's still going to be that bottleneck distance. All right, so here is another example. Okay, so this is an example. It's kind of clear what I'm doing when I'm saying maximum of the births and maximum of the deaths. It's a little less clear what to do when I match to the diagonal. And so here I have A is some point off the diagonal, okay, as a birth and a death value, and B is the diagonal, all right, it's the empty interval, all right, or it could be a single, well, it's the empty interval, okay, and so what I want to do is I want to take an interpolating object. Well, certainly the death value has to be the death value of A in order for me to get that morphism going, and then I need to figure out what I want as its birth value. And so what the trick is to say, all right, I'm going to take the midpoint. Okay, so I'm going to make it live half the time of A. All right, so this is just like in here saying I'm wanting it to be over here. All right, just over there. Okay, I hope you guys see the cursor. And so again, the kernel and the co-kernel will be corresponding to, will either be empty because there's no kernel from C to A, for example, or they're going to be at one interval half the length of the interval at A. Okay, and so again, the bottleneck distance is going to be what we want it to be. Okay, so it's going to be half that, it's going to be that distance to the diagonal. All right, does anyone have any questions? Making people happy? I don't know. So the theorem is, basically, whenever you have two modules and you have some matching between them, you can create, as I said, taking these maximums of things, this span between A and B, okay? A span sort of induced by that matching, okay? And it turns out that the cost, okay, that cost of the matching, which is this is the PP cost of the sum of the matching, is going to be, for every point in the diagram, I take the distance. Oh, sorry, there should be a little p down here. The distance between the points in the matchings. This is actually going to be the sum of a bunch of p norms. So each of those changes in the births or changes in the deaths will appear in exactly one of these summands. Okay? Now, depending upon whether A is inside B or B is inside A, or whether A is shifted entirely in front of B or shifted entirely behind B, which combination of these kernels and co-kernels and I and J will be different. They might be both in the kernel of I and the kernel of I, or it could be that it's in the kernel of I but the co-kernel of J, but they will both appear in exactly one of these summands. And because we're doing these p norms, we don't actually care which of these summands they come in because they've been divorced. Okay, if I had a q down the bottom here, I wouldn't be able to write this equal sign because I'd have to think of the max, and then that would take into consideration which of these it would be, and I would have a problem because I'd want it to contribute to only one of these summands, not to both of them, and so it just wouldn't work. I wouldn't have this equal sign. I'd have an inequality. I'd have less than or equal to, but I wouldn't have equals. The slightly harder thing to prove is to show that whenever you have any span, then your Wasserstein distance is bounded by these sums. So you have to look at induced matchings and things like that. It's doable, but it's much more ugly. But that's sort of the other side of the proof. And when you combine these together, it tells you exactly, whoops, there's a bracket missing, that the Wasserstein distance between the two diagrams of the persistence modules is exactly the infimum over all spans of these sums of kernels and co-kernels, p norms. Oh, there should be a p power. Wow, this formula did not work for me. There we go. It is the minimum of the spans. All right, let's go to the next page before anyone sees it too much. Sorry, does anyone have any questions about this algebraic interpretation? Yes, no, happy? All right, it is really blurred in these online talks. Okay, so the last thing I want to mention, so this is going a bit more back to the stats, is that central tendencies, mainly the mean and the median, are much easier to compute and just seem much more aesthetically pleasing when we make Q equals P, all right? So we can think about the mean and the median as being locations that minimize certain cost functions. Okay, so your cost function might be the sums of distances or sums of distances squared. Okay, so the mean is a minimizer of sums of distances squared. I mean, this is a way you can define it. You can certainly define it as the average, but a sort of nicer, more general way to define it is in terms of minimizing this cost. All right, so if I have a bunch of real numbers, all right, I can say, well, if for any other number, I can say, well, what is the sum of the distances squared to each of this set? All right, so if I take that function, it will be minimized exactly at the average. All right, and so I can say, well, the mean is that thing that minimizes that cost. All right, so the Frechet mean, if you want to be fancy. So the Frechet mean is going to be the thing that minimizes the sums of distances squared. All right, so you can define this for the real line. You can define it for points in Euclidean space. You can define it on a manifold. You can define it on any metric space, basically. Whether it's computable or not will depend upon how nasty that metric space is. Whether it's stable or unique will depend upon how nasty that metric space is, but you can define it. Okay? But notably, it does depend upon this D. Okay, so I've written D here suitably and with the ambiguity here. I have a metric space, it has some distance function. All right, so my choice of mean is going to be dependent on what that choice of distance function is. If I change my distance function, my mean will change. Okay, this is not controversial. So median can be defined sort of analogously to the mean. So I just look at the sums of distances rather than sums of distances squared. Okay, so if I have real numbers and I have an odd number of real numbers and I put them on a line, the thing that will minimize the sums of distances will be that sort of middle value in terms of order. Okay, so you can show that that will be the unique minimizer in the case of an odd number of samples. If you have an even number of samples, then there's a whole interval of choices that will be equally good, and you have to have some convention to decide which of them you take. Okay, usually the midpoint. So that's sort of the Frechet version of what a median is, and that again can be defined for any metric space. All right, so you're just looking at the point that minimizes the sums of distances. Okay, so I guess the reason why I've written connected here is just because if it's not connected, then you're going to have an infinity somewhere, no matter which connected component you pick, and you're screwed, and it's just too hard. So, but the key thing is means are minimizers of distances squared. Medians are minimizers of sums of distances. Okay, so if we want to go to persistence diagrams, we then need to think about how we're going to do these distances. Now, whenever we do a distance between some candidate location, some candidate persistence diagram, and all the other things in the sample, well, I'm going to have a point that goes to each of them, all right? So I'm going to have a point in diagram X1, a point in diagram X2, blah, 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 within my optimal matching between them. And so every point in my candidate mean or median is going to select exactly one point from each diagram. And so we're going to call that a selection. Okay, so this is sort of the notation from that fuzzy means paper by a whole bunch of people, mainly Liz. Okay, and so just to keep the notation and vocabulary going, if I want to take a bunch of these selections where every point is used exactly once, I'm going to call that a grouping. So I've got a whole bunch of persistence diagrams, okay, and I have some candidate. I look at an optimal matching, and that's going to basically partition all the points into a set of selections, where in each selection I have exactly one point from every diagram, but that point can be the diagonal, okay? So this is just sort of going down this route of trying to understand what a mean or a median of a persistence diagram, or set of persistence diagrams should be. All right, so let's think about the candidate, whoops, oh yeah, that's all right. A candidate for the mean. So you can see that I was doing these slides this morning and I copied and pasted from median to mean, and some of the things didn't change. I have a selection, and then I have to think, well, what is the mean of this selection? Well, it's going to minimize the sums of distances squared within that selection. So I have a multi-set within the plane union the diagonal, and I'm wanting to say, well, what's the minimum of the distances squared? All right? And then for every grouping, I can say, well, I have a set of selections, and in each selection I have a single point, which is the mean of that selection, and that will give me a persistence diagram. And I'm going to say, well, that's my candidate for the mean from this grouping, all right? And so every mean is going to, each mean will be some candidate from some set of groupings, all right? So then the question becomes, what is the mean of a selection, okay? So the P is basically determining that it should be the sum of distances squared. The Q is telling me what my distance is, what that metric is within that cost function for just doing what is the mean in the selection. So if my Q is P is 2, all right, I'm looking at basically Euclidean distances. So here I have an example, okay, a picture where I have 3 points here, all right, the circle, circle, and circle, and I have a copy of the diagonal, all right. Then what will happen is that the triangle, that black triangle, is going to be the mean of that selection, all right. So I'm sort of thinking quite geometrically here. I'm taking a weighted average of the square, which is the average of the off-diagonal points, and the point closest to the diagonal, all right, and that will give me what my mean is, all right. Now, if I take Q not to equal 2, all right, if I take Q equals infinity, I'm going to have to find a point, y1, y2, which will minimize the sum of the maximum of the differences squared. I don't even go to what that is. That's some gross formula, and I don't want to think about it, all right. Median has the same story, okay? I have a selection. This one shouldn't have the typos, thankfully, because I copy and pasted from this. So I have a selection, and then I want a median of that selection. Okay, so the median of the selection is going to be the thing that minimizes the sums of distances, okay? So again, it's dependent on that choice of Q, all right? And I have those groupings, which are those sets of selections, and then my candidate median from that grouping is just going to be that multi-set that comes one from each selection. Okay? So then the question in terms of computation is going to be, well, what is the median of a selection? Okay? So what I need to do, so let's think about what Q can be. If Q is P is 1, all right, that's what I want to argue it should be. Okay? Then I need to minimize, there should be a sum here, unfortunately. I need to minimize the sums of distances in the x, the first coordinate, and the sums of distances in the y's in the second coordinate. So x or y is an unfortunate choice. The first coordinate, second coordinate, but it means that we're effectively doing a median for each coordinate separately. I can take this problem, which was a 2D problem, and make it 2 separate 1D problems, which is a much easier thing to compute. Okay, so here I have an example where I have a triangle, a diamond, a square, and 2 copies of the diagonal. All right, so when I want to do this, I'm going to say, well, the x coordinates become effectively square, then diamond, then triangle, and then infinity and infinity, where I've put infinity in for the diagonal. All right, you can do these sums to see that infinity is the right choice. And so if I want to look at the x-coordinate, well, I can say, well, the x-coordinate should be the x-coordinate of the triangle. All right? And then if I want to do the y-coordinate, I do the same thing, but I do minus infinities for the diagonal. So I have a minus infinity, a diamond, a square, a triangle. And so I can see that the y-coordinate should be that of the diamond. So here, this sort of black circle is exactly the median of this selection. Now, if you don't have copies of the diagonal, it's easier still. You just literally take the median of the x-coordinates and the median of the y-coordinates. This sort of use of infinity and minus infinity is kind of analogous to that weighted average to the mean in a way. You're sort of weighting how far along in your order you count your median to be. Okay? So if I took Q to not be 1, all right, I'm going to just compare to two different things. So one thing is I could take Q to be 2, all right? This has a name. This is called the geometric median. It does exist in computational geometry. It is known to be hard to compute. I think once you go beyond 5 points, it's very hard to compute what the geometric median is. I think if you've got like 3 points, then there's triangle things you can do. But if there's enough points, it's very hard, known to be hard. If you take Q to be infinity, you have to minimize the sum of maximums of various things, and that's just gross. So I guess generally, if you take Q to be infinity, this median of selections is going to be gross. So that overall structure of you split your points into, partition your points into different selections and you do stuff, that's sort of independent of your Q. Okay, the actual cost for each grouping would be different, but that concept would still be true. But then when you get to the selection, that sort of itty-gritty locally what happens, you really want your P to equal your Q so that you can kind of split them into different coordinates. All right, so I'm just going to finish off by appealing to people to make the switch. Consider Q to be P. It doesn't take that much. If you code distances, you replace one line of code. If you do nothing else, if that's all you do, then other people have the choice. I think a lot of people use Q equals infinity because that's what the code has. If you're performing statistical analysis, you have a bunch of persistence diagrams, you're wanting to perform statistics or something, or do some sort of more analysis-y type things, I would argue that you should use Q equals P. You can bask in the stability results, the sensible mean median, and just the much nicer formulas. And if you're doing theoretical work, if you're thinking, categorically or functorially or algebraically or whatever, if you switch to Q equals P, then all of a sudden you have all this algebra you can work with as well, which I think would be much more powerful. So that's the end of my talk. This is my plea. I hope I've convinced at least one person here that Q should equal P. And I'm happy for questions or comments.
Okay, thank you. Questions for Kate? Anyone? Yeah, so remember, if you want to ask a question, unmute yourself.
There's a question that was chatted in. Are there applications to point clouds in particular?
Well, so if you're thinking about the stability results, then yes. So one of the unfortunate things about the previous LP stability result that was out there was that it did not apply to RIPS complexes. It very much specifically did not. And some people have misinterpreted this and applied it to RIPS complexes. But yes, so Primož and I have been working on stability results involving RIPS complexes, which is, I guess, the most common thing for point clouds. So certainly, sorry, there we go. As a basic corollary of the Lipschitz stability for simplicial complexes, you can also get Lipschitz stability for the Rips complexes on a set of points where your Lipschitz constant is dependent on the number of points, which is kind of gross, but you get that kind of, well, not quite for free, but it's less massaging. What is more difficult is trying to find a Lipschitz constant that is independent of the number of points. So this is true for certain homology and ambient space dimensions, but you can also find counterexamples for others. So I think that that's sort of an interesting area in terms of you want to say, well, the distance between the persistence diagrams for the Rips complex is bounded by, I think it's 12 times the distance between the point clouds in a sort of p-Wasserstein sense of the distance between the point clouds whenever you're looking at H1 in R2 or something. The exact number, it may not be 12, but there's like concrete numbers, and that's independent of the number of points. It's basically to do with what kind of bounding, how much local behavior you can have around a single point. So if you were to shift it, only so many critical cells have so many points in the diagram are kind of going to contribute to that difference in the Wasserstein distance between the diagrams. So certainly there's some work towards that. I think that there would be other things for check as well, but I think that's harder because they're not determined entirely by the edge lengths. You know, you have to, well, I guess they are entirely determined by the edge lengths, but not by a very straightforward, I add in the edge and then everything happens kind of way. So yes, there are some stability applications to point clouds.
Okay, any other questions? Okay, so if there are no questions, how about
I want to ask another question. Sorry, I'm hogging all the questions. I have one other question. So I mean, Kate, you were sort of thinking in the sense of you have persistence diagram points and you're sort of computing Wasserstein distances between them, but there's a diagonal there and there's an interpretation there of persistence diagram points. I was wondering which of your 5 arguments sort of hold in the setting where you just have 2 finite probability measures in the plane, you know, sums of direct delta masses, and you're just there's no diagonal and there's no interpretation of coming from births and deaths. I think 1 still holds, number 5 still holds, and maybe like
well, so I mean, the persistence modules are not a thing in this case, I guess.
Yeah, persistence 4 makes no sense. 3 doesn't really make sense. 2 is sort of like if your coordinates still have some meaning, then
you can. So it's unclear. Yeah. So if your coordinates don't have meaning, then much of this is not relevant. Much of this does depend very much on the fact that your coordinates do have special meaning and that we should respect that. Mm-hmm. Yeah, so certainly the formulae are still nicer and the central tendencies are much nicer, but the others are less relevant. So I would argue that you should be using whatever the standard metric is in, you know, if it's the plane, then probably keep Q to equal 2 if it's just points in the plane and the coordinates don't have meaning.
I see. Great, thanks so much.
All right.
Okay, great. So if there are no further questions, I mean, and there can be questions offline. I mean, like once we're done with the recording, then I would ask everyone to unmute themselves so that we can clap for Kate. Thank you again, and we'll see you all next Wednesday for Omer's talk.